Sean Monkman, who is a representative from CarbonCure Technologies. And Sean is giving us a presentation on industrial application of in-situ carbonate nanoparticle seeding. Thank you, Sean.
Okay, thanks, John. Okay, I'm going to talk about what we're doing at CarbonCure, which is easily described as using in-situ carbonate nanoparticle seeding to create better concrete. I'll cover 4 things in the talk. I'll introduce you to the concept. I'm sure many people aren't aware of what this means. I'll get into some of the industrial results, talk a bit more about the value proposition, and then explore the mechanism as understood currently. So what we're doing is we're taking the concept of CO2 utilization and pairing it with ready-mix concrete production. And CO2 utilization is a process where you turn carbon dioxide into a feedstock for another product. In this case, it's a component used in a concrete mix. And what is being offered is a retrofit technology that is installed at a concrete plant. So what you can see here in the big silver tank, that's liquid CO2. There's a small control system beside it. And then the CO2 itself will be injected through the line up into the mixer or the truck mixer or the central mixer at a concrete plant. There'll further be a control system in the control room to make sure this is integrated into the batching process. But what we're doing is we're taking carbon dioxide and injecting it into the concrete as it's being mixed and batched. And it's meant to be done in a very scalable and easy to adopt fashion. The small amount of equipment that shows up to manifest this technology is just a very incremental modification to the concrete production process. And the producer can use the same Portland cement and sand and water and everything else, mixers and so forth, that they were already using. So it can be installed, in one morning and up and running in the next day. What does this mean when you're injecting CO2 into a batch of concrete? Well, if you're taking liquid CO2 and you're sending it into anything else, it's kind of like a fire extinguisher. The liquid CO2 is not actually stable at atmospheric temperature and pressure. So what meets the concrete is actually a mixture of solid CO2 and gas. And so this looks just put on the ground, a CO2 injection system for purposes of visualizing what comes out the end of the nozzle. So this would be fixed into where you're batching the concrete, either into a central mixer or into a truck, much like any other mixed component that ends up going into either of those 2 things. So if you had to visualize it, the easiest way to do so is to think of it in terms of admixtures. So when you're making a batch of concrete that would start in the batch house, they would say, I need, for example, 9 yards of a 4,000 PSI mix, and it's got 25% fly ash, and it's air entrained and so forth. So they would send the recipe into the process to put these components into the concrete mix. So in the admixture approach, you would have a supply of admixture, which is then told by the batch controller to be put into the product. So the dispensing system measures the precise amount of admixture, and then it puts it into the concrete. Much the same way, you have the CO2 supply, as I showed. There's a big tank sitting there in the vicinity of the concrete mixer. A CO2 dosing unit is the component that controls how much, when, and for how long the CO2 is put into the process, and it just gets mixed into the concrete. What happens when it gets there? Since this is at the various earliest moments of concrete's life cycle, right in the mixing stage, we would start with water meeting cement, and you get some dissolution. When you add CO2 to the system, well, it's starting outside of the solution. It's a mixture of solid and gas, but just the way science goes, upon exposure to the solution, it will go into solution and form a carbonate ion. And what happens is the carbonate ion finds its most stable form partnering up with calcium carbonate. So you get this near spontaneous mineralization. You form calcium carbonate particles. And what you're forming is a very stable form for CO2 or carbon. So it's going to stay that way. unless something unusual happens to the concrete, such as extremely high heat, enough to calcine the calcium carbonate or some concentrated acid. But for all intents and purposes, this mineralized CO2 is now permanently stored into the concrete. And what happens is that you actually catalyze the hydration. So you can see, and I'll show some pictures later, you can see the formation of calcium silicate hydrate gel is really kicked off. What has this meant industrially? There's almost 300 users of this technology across North America, Canada, Singapore, soon to be South America and Europe. But they'll put a dose of CO2 into the concrete, much like other nanomaterials, or much like nanomaterials. The dosages used are very small. So as reported along the bottom, we're looking at dosages from 0.1 to 0.25% by weight of cement. You can see at the early ages of 1 to 4 days, you have a dosage sensitivity. In this case, you have an increasing performance gain as you go from 1.1 to 0.2%, and if you go a bit higher than 0.2%, we're starting to go down the other side of a performance curve. So possibly based on this, you would select an optimum dose in the 0.15 to 0.2%. In this case, you're getting somewhere between 10, almost up to 20% compressive strength benefit across this time period. This performance lasts through 7 and 28 days and beyond. So you have now an addition of CO2 is giving you stronger concrete. And if you could dial in the right dose, then you can leverage that for mix optimization. And this dose itself is not that different from conventional chemical admixtures, let alone nanomaterials. So in many respects, the chemical aspects of this is much like an admixture. So if you have additional strength, then you can actually use that as a basis for a mix design adjustment, because somebody that's making concrete doesn't necessarily need to give the end user stronger concrete. They just need to give them strong enough concrete. So what they're concerned about is not the average strength. They're concerned about the strength that's at the bottom end. So where they can be 95% certain that the batch of concrete goes out will be stronger than the strength that's needed for the job. So in this case, if you're doing something that gives you stronger concrete, you can do something that makes an adjustment to give you, again, strong enough concrete. So in this case, what they've done is they've taken out 5,000 PSI mix. I guess I'm mixing units. I've gone metric on the mix design, but they've taken out 5.5% of the cement. So if you look at the CO2 impact on the binder, you're reducing it by, what is that, 17, 18 kilograms per cubic meter. You've improved the binder intensity. You've improved the carbon intensity of the mix. So by adding a small amount of CO2, you've been able to reduce a much larger amount of cement, and with the cement comes the environmental benefit. So the environmental benefit is not so tied up in the CO2 mineralization itself, but comes with the avoided Portland cement. Now, to make this viable, you can't be doing anything to the concrete producer that's going to cause problems downstream. The air content is not changed by addition of the CO2. The air content in the concrete is not bubbles of CO2. As I'll show you, it's mineralized CO2. The workability is not changed either. So you have extensive producer data verifying that the fresh properties is not changed. And while I won't talk about the durability impacts in this presentation, they are also have been assured through testing. So what's actually going on here? So there's been some mechanistic investigation to better understand this. And then we start with a hypothesis that we've created some nanoscale calcium carbonate, and it's acting in the nucleation site for hydration process. We can see this in isothermal calorimetry, not included in this presentation. And as I've shown you, we can see this in macro property of compressive strength. So this is an example of an SEM picture of a CO2 injected with can't remember if it's cement or tricalcium silicate, but in either case, what we're seeing is an approximately cubic particle that is formed in the concrete or in the binder system. And this would have been hydration arrested within a minute, maybe 2 minutes of the injection of the CO2. So this is very early stage hydration. So what that looks like in a broader sense, I guess here's my details. It's tricalcium silicate. We've added CO2. In this case, the water to solids for purposes of injection was quite high, as 1.2, just a modeling exercise. After 90 seconds of mixing and hydration, including a CO2 injection over the last 50 seconds, we arrest the hydration, and then we see these particles which are observable within the carbon-treated, CO2-treated system, but not the reference hydrated system. If you look at a system like this a few minutes later, in this case it was a slightly different study, again, tricalcium silicate, this time the water to solids was a bit lower, but we can see observations within the CO2 activated system that we're getting a lot more of a gel face forming even at 5 minutes. And so we do not have necessarily the reference concrete in the presentation. I should have put the paper reference on this slide, I apologize, but this is a net difference in the amount of products and the timing of these products versus the reference case. So we've also looked at the products under TEM. So this is a surface product on a C3S. And so if you did the dimensions, it's more or less a platelet, 250 nanometers across and 85 nanometers high. But you can see it might also be a collection of a bunch of agglomeration of smaller particles. We can see that in the interface between the particle and the C3S substrate. With having identified these products, we did a slightly different test. So this would be an SEM, but we've took a C3S particle, created a calcium or a chromium coating on an area of interest, and then took a cross section. So we're getting a picture of the interface between the C3S and the surface. And then we used what was a novel technique called atom probe tomography. I know they've done this at Northwestern. We did this at McMaster. Oh, I didn't fill out the footer. I apologize. And what this technique is doing is you take this sample that you've made with the focused ion beam, you take out a slice, and then you mill it down into a needle. And that's, you can map that back onto the original specimen there. You take a section of it. And what you do is you put it in the atom probe tomograph, and you basically destroy the needle shape from the tip downward. And as each atom flies off the tip, you can actually characterize it in terms of what type of atom it was and what location it had. So through this exercise, you can see the needle has a protective tungsten cap on the bottom, then there's a chromium layer, and then we get into the sample. So if we focus on that sample, when we analyze it, it looks something like this. So we have a volume investigated of the C3S, and shown in red is where we found a high carbon concentration. So right near the surface, we've got this blob of a calcium carbonate particle, and the dimensions there are in nanometers. So now that you've got this information, it's just stuck in a computer, all these different atom locations and identities, you can actually do profiles in all sorts of different directions. So if you looked at where you define your baseline as either inside the particle or outside the particle, so if you're going even a few nanometers outside the particle, you don't have carbon. If you go a few nanometers into the particle, you do have an increase of carbon. In this case, it's around 40 or 50%. On the other hand, if you look at the calcium is dropping as you go into the calcium carbonate particle, or it's more dilute. The silicon doesn't really do much itself. It's not, it's present at a small level outside the particle. It's present at about the same level inside the particle. So that would imply there's a intermixed character of the calcium carbonate and the silicates. And then you have the oxygen plopped in there. So within this information, we're able to better characterize what have we formed. We'll start to use this information to look at the sensitivity of cement chemistry and better understand the kinetics of the process that's going on. So I'd like to wrap up this presentation by saying thank you, especially to the presenters and ACI for putting this event on nonetheless. And I have mentioned some of this work was done at McMaster, so I extend thanks to them and to the National Research Council in Ottawa in Canada. Thank you.
Oh, well, thank you for that talk. And it looks like we've got a few questions. How can we use the CO2 to enhance the concrete performance without increasing the corrosion of the rebar?
This is such a good question. I actually have an appendix to my presentation. It comes up so frequently. So just to comment on the durability, which is the other question. We've tested it many times with no adverse observations. But when you talk about carbonation in concrete, the first thing that many people think about is atmospheric carbonation. And that can be a durability problem because you have a mature cement paste system that contains calcium hydroxide. The CO2 comes in, converts the calcium hydroxide to calcium carbonate, and then you lose the alkalinity because you have less calcium hydroxide. However, that's not what's happening here. Starting on the right, this is industrially produced concrete with the pore solution extracted at 56 days, so there's no difference. The CO2 has done nothing to the pore solution alkalinity. And if we go back to the left, this is because of when the CO2 is added, you have a very fresh system, so the system can rebound. You've taken some calcium out of the calcium balance of the entire system, and yes, the pH goes down. It goes down about a half a point or so, and it only goes down for about 20 or 30 minutes, and you haven't even set your concrete yet. So you have this idea where, yes, you are impacting the pore solution a little bit, but it's not something that persists, and it's not something that has any impact on the pore solution pH or the durability thereof.
Cool. I think we have time for one other question. Good presentation. How about the pH value of the CO2 added to concrete? Do you worry about oh, well, that's just asking the same question. Do you worry about
I told you it was a good question.
It is a good question. It's a great question. I mean, do you want to further comment on that, Sean?
No, I guess that's just part of the misconception between concrete carbonation and CO2 utilization for concrete. And if you go to the website, we do have a few like white paper type of explanations of our understanding of the differences.
So can I alter that question a little bit, Sean?
Yes, of course.
So instead of asking about the pH value of the CO2, is there a concern when it comes to other supplementary cementitious materials that might consume some of the calcium hydroxide, and of course not making that available for that CO2 calcium carbonate combination?
Interesting question. I suppose if you looked at it as some calcium went somewhere else, and what does that mean for everything else in the system? We have looked directly at the amount of calcium hydroxide that's formed in the absence and presence of CO2, and there's really no difference. So if you're looking at something that is activated by the alkalinity of the system and consumes calcium hydroxide, there should be no difference.
Okay. Okay. Well, thank you very, very much, Sean. Everybody give it up. Yeah, it's kind of hard for everybody to give it up, but everybody's clapping for you, Sean. That was an awesome presentation.